This is the equipment that's needed to perform your next lab, Newton's second law in force. As you can see, we have another crash cart, but in this case, this crash cart has a plunger on the front. Primarily, we want to use this one because it has a thing on the top that we can attach a string to. We have a set of masses, along with a pulley, a sound sensor for data acquisition of motion, 1 meter's worth of string, a track, a 250-gram mass, and for the case in which we double the mass, a 500-gram mass. The next video will show you what it looks like when it's set up. This is the experiment when it's been set up properly. As you can see, you have the plunger cart right here. I've put a mass here to keep it from running while I film. We have our sound device, which is a digital sensor. As you can see, it attaches to the digital side of your device for acquisition. On the top of this, you have two modes. You have a cart mode and you have a person mode. The difference between the two is how tight the beam is focused. Because carts are small objects, we want to make sure it's set on the cart mode. When you do your runs, you want to make sure that your cart is no closer than about 15 to 20 centimeters from the sensor. What that does is to help prevent weird scattering and data acquisition. On the end, you have a 20-gram mass. The hanger itself, as you can see on the side, very, very vaguely, has a mass of 5 grams. You'll be doing 3 runs. One with the cart as it is, one with the 250-gram mass on the cart, and then one with 500 grams of mass on the cart. This is what a run looks like. Now, in this case, what I've done is to take the 500-gram mass and put it down on the edge to simulate having a partner help me do the experiment. In truth, the partner would probably be there to catch the cart so it doesn't fall off the edge. Now, you release the cart from rest, allow it to go down the track and to hit the end. When you do this, you'll actually be doing this experiment 3 times. You'll do it once with the cart by itself, then once with a 250-gram mass, and then one with 500 grams.
This is the theory section for Lab 3. Now, Lab 3 is similar to a problem that we've worked before, which is a car with a mass with an additional mass attached to it that hangs over a desk over a pulley. So if you think of it like this, where you have a table or a desk like that, and here's your pulley right here, we'll say. Here's your cart right there. And your mass hanging off like this right here. We know from our discussion about forces that the weight of the mass below is conveyed up to the mass above via the tension that's inside the string. So in this particular problem, we're going to ignore the mass of the string. That's generally accepted unless you're explicitly told that's going to be the case. So we'll call this right here the mass of the cart, and this is the mass of the hanger right there. So, like I said, we've solved a problem like this before, but just to do it again, what we're going to do is we're going to draw 2 force diagrams here. One for the cart and one for the hanger. I'll call this the cart. This is the hanger. And if you look at the cart, we know the cart has a weight pulling it down like this. We know that as a consequence of it sitting on the table or on the track in the experiment, that there is a normal force that goes up like that, and then there is a tension that goes down the string like this. For the hanger, we know that there is a force going up That's the tension that's balancing out the weight of the hanger that's going down like that. So for the cart, if we were to draw, just go ahead and label the axes right here, y and x like that. For the cart, you have a normal force going up, a weight going down, and then the tension going off to the right. For the hanger, you have a tension going up, and you have its weight going down like that. So let's label these things. Normal force, the tension, the weight of the cart, like that. And let's not forget that the tension inside a rope or string or whatever, it's the same at all points. So this tension and magnitude is the same as that tension and magnitude. The direction is just different. We also have the weight of the hanger right here. Now, the idea is that it's the weight here that's going to provide the force that's required to move the entire system. Because remember, these are composite objects, right? So if you were, to look at Newton's laws, or Newton's second law rather, and sum up the forces here to get the net force, we'll say on the cart, you would have three. You'd have a normal force, you would have the weight of the cart, and you would have the tension that's inside the string. Now, these are going to add up to give you the mass of the cart being accelerated, right? For the hanger, when you add up all the forces that you have present, you have two. So here's the net force on the hanger. You have a tension going up, and you have the weight of the hanger going down. And these are going to add up to cause the hanger itself to experience acceleration. Now, the deal here is that the directions of the acceleration are going to be different, but the magnitudes are going to be the same because these objects are linked by a string. So if I were to pull this thing down with an acceleration, this is going to experience the same acceleration to the right, we'll say. So for the cart here, if I look at what's going on in the y direction, there's really nothing interesting. The normal force is going to balance out the weight of the cart since the cart isn't bouncing up and down as it slides to the side. We also have, in the x direction, a tension that's to the right, and what that tension does is to act on the mass of the cart to cause acceleration to the right. I'm just going to call it A. It should be A sub x, but the A in magnitude here is going to be the same as the A in magnitude for the hanger. Now, for the hanger one, we have nothing interesting at all going on in the x direction. But if you look at what's going on in the y direction, we have a tension that points up, we have a weight that points down, and these things are going to act on the hanger itself to cause it to experience acceleration. Now, the accelerations, like I said, are the same in magnitude. I'm going to put a minus sign in here to denote the fact that I know that this is going to experience acceleration downwards. Now, they're linked through tension, as you can see. T is equal to m sub c times a. It's an unknown, so I could plug this into that and link the two objects through tension. So if I do that, taking this equation right here that says the tension minus the weight of the hanger is equal to minus m sub h times a, and I plug this into it right there, then I get the mass of the cart times the acceleration that it experiences minus, now let's go ahead and take and plug in what the weight here is. Weight is m times g. This is the weight of the hanger, so that would be m sub h times g. That's equal to minus m sub h times a. And all I'm going to do is to take and move this over to the left-hand side and move this over to the right-hand side. So when I do that, I get mass of the cart times the acceleration it experiences plus the mass of the hanger times the acceleration that it experiences is equal to the mass of the hanger times the acceleration due to gravity. Let me fix that real quick. Sorry about that. There, like that. Now, so the important thing is what this is basically telling us. If I take and I pull the A's out, I have the mass of the cart plus the mass of the hanger times A. On the right-hand side, I've got this. This is the weight of the hanger. So the weight of the hanger is causing both of the masses to move, and as a consequence, they experience an acceleration. That's basically what this is saying. So were you to write that out, the acceleration that you would have here would be the mass of the hanger times the acceleration due to gravity divided by m sub c plus m sub h. So this right here is the equation that we're going to be working with. Now remember, the idea here is that you're going to take, three measurements. You'll have one measurement with, the hanger at 25 grams, and then, the cart, which I believe was 623 grams. You'll have to check the lab for that. So you're going to do one run like that, and then you're going to add 250 grams of mass to the cart, do the run again, and then add additional 250 to the cart and do the run again. And as you can see, as the mass of the cart goes up, the overall acceleration should go down, although it's not going to be zero. Okay, so this is roughly how the math works in the lab.